Hey, welcome back. Today, we're talking about an element that's, well, it's everywhere. It's in the air we breathe out, it's the foundation of the food we eat, and it's literally the code that makes you, you. It is the ultimate architect of life. So let's get into the incredible story of carbon. Okay, so our story actually kicks off with a real head-scratcher, a puzzle that, on the surface, just doesn't seem to make any sense. We're calling it the carbon paradox. And here's the big question that gets us started. How on earth can an element that's actually super rare in our planet's crust be the absolute, fundamental building block for every single living thing we know of?
I want you to look at this number, 0.02%. That's it. That is the tiny, tiny fraction of the Earth's crust that's actually made of carbon. You know, stuff like coal, petroleum, and certain minerals. It's practically a rounding error. And yet, just look around you. Everything from the food you eat, to the clothes on your back, to the medicine in your cabinet, it's all built on carbon. Every living thing we've ever discovered is a carbon-based life form. So what's its secret? How does it do so much with so little?
All right, to crack this case, we've got to zoom in, way in, down to the atomic level. Because the first big clue to carbon's secret is all about how it plays with other atoms. It has this really unique way of making friends. Let's see how it works. So, to really get what makes carbon special, you've first got to understand this basic choice that atoms have when they get together. Most of them will either give away their electrons or straight up steal them from someone else. That creates charged particles, or ions, and we call that an ionic bond. But carbon? Nah. Carbon plays a totally different game. It prefers to share, and we call that a covalent bond. So why share? Well, a carbon atom has 4 electrons in its outer shell, but it's not happy. It wants 8 to feel stable. So it's kind of stuck, right? Gaining 4 more electrons is a tough ask. Its nucleus is just too small to hang on to that many. And losing all 4? That would take a ridiculous amount of energy. So it's left with this one beautiful, elegant solution. Share. And this sharing, well, that's what we officially call a covalent bond. It's this perfect arrangement where 2 atoms share their electrons so that both of them feel like they have a full, stable outer shell. It's a win-win, and it creates a really strong connection without any of that messy ion stuff.
Just look at methane here, CH4. It's the perfect example. You've got the one carbon atom right in the middle, and it's sharing one of its 4 outer electrons with each of the 4 hydrogen atoms. Everybody's stable, everybody's happy. And this simple, brilliant act of sharing, well, it's the key to absolutely everything else.
Okay, so this sharing thing, it's not just a neat little trick. It's what unlocks 2 incredible, almost magical properties for carbon. You can think of them as its chemical superpowers, and they're what make it the ultimate building block of life. All right, superpower number 1, catenation. I know, it's a fancy word, but it just means carbon is amazing at linking up with itself. It can form these super strong, super stable bonds with other carbon atoms over and over and over again. Honestly, it's like the ultimate Lego block, right? It can just keep connecting to other identical blocks basically forever. And you can see it right here. You start with 1 carbon in methane. Then, boom, ethane links 2 of them together. Propane links 3, butane 4, and these chains can get incredibly long. This ability to form these stable carbon-to-carbon bonds is something no other element can do nearly as well. Superpower number 2 is called tetravalency. Tetra just means 4. And because carbon has those 4 electrons to share, it means it can form 4 separate bonds at the exact same time. It's like it has 4 hands, letting it grab onto 4 other atoms and build these complex structures in 3 dimensions. So you take superpower number 1, catenation, the ability to form long chains, and you combine it with superpower number 2, tetravalency, the ability to branch out in 4 different directions, and what do you get? An absolute explosion of possibilities. Together, they allow carbon to form millions and millions of different molecules. So what can you actually build with an element that has these 2 superpowers? Let's take a quick look at the sheer architectural genius of carbon, because the answer is pretty much anything you can imagine. Check out butane. Its formula is C4H10. Simple enough. But because of carbon's building ability, you can arrange those exact same atoms in 2 totally different ways. One is a straight chain, the other has a branch. They're made of the exact same parts, but they're built differently, and that gives them different properties. We call these structural isomers. And it doesn't just stop with chains and branches. No way. carbon's ability to link to itself is so strong that the chain can actually loop back and connect to its own tail, forming these incredibly stable rings like you see here with cyclohexane. This just adds a whole other level of complexity to the things it can build.
And if you want the ultimate proof of carbon's versatility, this is it. Diamond and graphite. Both of them are 100% pure carbon. That's it. But in a diamond, every carbon atom is locked into a rigid 3D grid with 4 neighbors, making it the hardest substance we know. In graphite, they're bonded to 3 others in slippery sheets. The hardest thing in the world and the soft stuff in your pencil are the exact same element. It's all about how it's built.
But here's the thing. Carbon's story isn't just about how it bonds with itself. It's also, as the source material so perfectly puts it, a really friendly and social element. It absolutely loves to form strong, stable bonds with a whole bunch of other atoms too.
And I just love this phrasing from the source material. It really captures this next piece of the puzzle perfectly. Carbon isn't a loner. It goes out and makes friends, forming compounds with all sorts of other elements. And that's absolutely crucial for the complexity of life. See, by forming these strong bonds with elements like oxygen, nitrogen, and others, carbon creates what chemists call functional groups. You can think of these as little attachments or accessories that clip onto a carbon chain and give the whole molecule a new personality. You add an oxygen and hydrogen group, and bam, you've got an alcohol. The social nature is what creates whole new families of compounds.
So, let's put it all together. Let's solve the paradox. Carbon's incredible success isn't some cosmic accident. It's a direct result of its unique chemistry. It has that clever workaround for its electron problem by just sharing. It has the superpower to link to itself in endless chains. It has 4 hands to build complex shapes, and it's friendly enough to form strong bonds with lots of other elements. And that, right there, is the final takeaway. The reason carbon is the architect of life has nothing to do with how much of it is lying around. It has everything to do with its incredible, unique, and unparalleled ability to build.
Which, of course, leaves us with one last kind of mind-bending thought. Silicon is right underneath carbon on the periodic table, so it shares some of these properties, but its bonds are weaker. They're less stable. So, if life could be built from silicon, what would it look like? Would it be crystalline? Would it move incredibly slowly? It's a fun thing to ponder. Thanks so much for tuning in.